Well, we've decided this mechanism can't be right. This two-step mechanism is impossible because it requires you to make the impossible primary carbocation. So it's not a multi-step reaction. The only reasonable alternative is that it's a synchronous, concerted, one-step reaction. So we go up and down once. Great. So let's start with that. We're going to go up. The question is, how far down do we go? In other words, are we an endotherm? Are we thermoneutral? Or are we an exotherm? Which one is it? Well, let's see what the players are. What have I done? I broke a carbon-chlorine bond. I made a carbon-carbon bond. Well, carbon is a lot smaller than chlorine, which means the carbon-carbon bond is a lot shorter than the carbon-chlorine bond, which means the carbon-carbon bond is a lot stronger than the carbon-chlorine bond. So it takes me less energy to break the long carbon-chlorine bond, and I release more energy in the formation of the shorter carbon-carbon bond. In other words, this reaction is an exotherm. So I have a concerted exotherm, starting with the chloride and cyanide, and I end up with propanonitrile and bichloride. And that is what my reaction profile diagram looks like. It's concerted, one step, it's an exotherm, which I know because the bond I make is stronger, more energy released, than the bond I break, less energy required. Let's do another one. Let's look at the reaction between let's say acetone in aqueous cyanide to give rise to this compound. This compound is called a cyanohydrate. So I treat acetone with cyanide in water, and acetone, of course, is miscible with water. I end up with a compound called a cyanohydrate. How does that happen? Well, laundry list. I'm going to figure out what happened in the reaction. Now this one is a little bit more complicated in the sense that my substrate doesn't necessarily look like my product. I'm going to figure out where my pieces are. So look, I'm going to take, the way you do that is you find an atom or a group that is preserved in the product, and you use that as a marker, as a signpost for what is happening. So I'm going to go with, let's pick the O. I have an O doubly bound to a carbon, which itself is attached to two methyl groups. O doubly bound to a carbon attached to two methyl groups. And O singly bound to a carbon attached to two methyl groups. So clearly, that O is this O. This carbon, the carbonyl carbon, is now that carbon. It's now a carbonyl carbon. These two methyls are those two methyls. Okay? All right. So I know I need to break the CO pi bond, because the pi bond is a lay bond. Okay, that's one thing. The O is attached to H. So I must make an OH bond. Two things. The cyanide, cyano group, is attached to my carbonyl carbon, which was once my carbonyl carbon. So I need to get the cyanide attached to this carbon. Three things. So I have three steps that need to occur, and I just have to figure out which one happens first. Okay. So I have a mental list: break the CO pi bond, make an OH bond, make a carbon-carbon bond between the carbonyl carbon and the cyanide. I'm going to make one change to this. I'm going to make this in, let's make this aqueous acid now. And I'll explain why. So I've got aqueous acid. So on my list of things to do, I've got to make an OH bond, break a carbon-carbon, carbon-oxygen pi bond, make a carbon-carbon bond. One of the truisms we will learn with mechanism is that the fastest reaction in organic chemistry is proton transfer between heteroatoms. Okay, let's just see what that means. So when I looked at the very beginning at hydroxide attacking HCl, and what we got was water and chloride. What happened? Well, I transferred a proton from one heteroatom to another. This is proton transfer between heteroatoms. That reaction happens at the rate at which bonds vibrate. That is infinitely fast. Well, not infinitely. It's about 10 to the 14 times per second, which is very fast. 10 to the 14 times per second, which is very fast. That is the fastest reaction in organic chemistry, quite simply because if I ask you to move the podium, and it's easier to push and pull, then moving this podium from one end of the room to the other might take me, with another friend, might take me 2 or 3 minutes. 2 minutes, maybe, because the podium is heavy. It's heavy. If I ask you to move the marker from one end of the room to the other, especially with a friend helping you, how long is that going to take? Well, that's very easy, because this is light. What is the lightest atom? Who's the lightest atom? The lightest atom is hydrogen. So reactions involving moving hydrogen, especially when they're assisted by a push and a pull, happen very fast. The rate at which I move this compared to the rate at which I move this, they are night and day. Moving protons is very fast. When the H is delta positive, and when will that happen? When it's attached to a heteroatom. And when the other heteroatom has a negative charge or is electron rich, so it has a negative dipole, that process is going to be as fast as a blink, faster than a blink. So the fastest reaction in organic chemistry is proton transfer, because protons are light, between heteroatoms, because that's when the H has a positive dipole and the heteroatom is electron rich. Okay? So proton transfer between heteroatoms is the fastest reaction in organic chemistry. So if I have 3 events vying for first place, make a carbon-carbon bond, break a carbon-oxygen pi bond, transfer a proton from O to O, heteroatom to heteroatom, Who wins? Well, the fastest reaction wins. So because proton transfer is the fastest reaction in organic chemistry, it is also the first reaction in organic chemistry. Whenever proton transfers are in the list they're in my list of to-do things, they're in my laundry list, they go first. Because proton transfers are the fastest, therefore in the competition between proton transfer and making a carbon-carbon bond and breaking a carbon-oxygen bond, proton transfers win. Because they're the fastest reaction. They're the easiest reactions. And if you're easy, then you're fast. So I know now that what I have to do is to transfer the proton from the aqueous acid to the O. I know that has to happen first. Okay, good. Well, how does it happen? Right? What am I doing? I am making an OH bond. Now, I'm going to tease this out. I am making the OH bond. What's my question? Where do the electrons for the bond come from? Well, they'll come from the electron-rich species. Well, who is that? It's not this. That's electron poor because it's positive charge. It has to be the O. And why will the O be electron-rich? Because it has lone pairs of electrons. Now, it's got two lone pairs. I don't have to draw them both. I just need to draw the one that is involved in the chemistry. But I must draw the electron pair. So I cannot, for example, just magically do something like this. I'm not showing the electrons that are involved. So I must show the lone pair of electrons on the O. Right? And remember we talked about this. Lone pairs of electrons are very nucleophilic. And I will also add that carbonyl compounds are in resonance with a form in which the carbonyl O is negative and the carbonyl carbon is positive. Which means this O is actually a decent nucleophile because I'm juxtaposing the lone pairs of electrons, which make me nucleophilic, with a significant delta negative charge, which accentuates my nucleophilicity. So here's where my electrons are coming from, the electron-rich O. Here is where they're going, between the O and the H. Well, the H already has a duplet. It's already bound to the O. So I must now break the HO bond. So I'm going to break the HO bond. Does that make sense? Yeah. That's electron-rich. There's a delta minus charge here, both because of the lone pairs and because of resonance. If that H is attached to O, just being attached to O makes you delta positive. Being attached to O plus makes you very delta positive. So it makes sense for the O to attack, for the delta negative O, rich with lone pairs, to attack the H. When the O attacks the H already is a duplet. It can't hold 4 electrons. So what will it do? Give this O what it has been demanding from the time they were partnered. It wants electrons. It's electron rich, it's electron poor, made worse by the positive charge. It is the sink. So the lone pair electrons will attack the H. I'm going to break the bond between the H and the O, and that's going to give me this species, O with an H on it, and I will lose, I'm going to put it here, I'll put it here, I'm going to lose H2O, H2O. Now, something is missing. The left-hand side of this equation is positive. There must be a charge somewhere. Where is it? And why is it there? Again, this O is neutral when it owns the lone pair. As it forms the OH bond, the O is in essence giving the H an electron. If I'm neutral and I lose an electron, I've got a 1 plus charge. That species with a positive charge on the O is called an oxonium ion. O that is hypervalent. It's got a valence greater than 1. In this case, the valence of O is 2. So this is a valence of 1 greater than 2. So it's a valence of 3. So it's hypervalent. And it's positive. It's called an oxonium ion. Okay. Reactions that are proton transfers are what we call acid-base reactions. We know that acid-base reactions are equilibrium. So I must now put an equilibrium arrow. And you're not required to indicate where the position of equilibrium lies, just that you recognize proton transfers, acid-base reactions, are equilibrium. There are 2 reactions you must know that are equilibrium. One is proton transfer. You get to the other ones later on. Okay, so what of my laundry list of 3 things have I done? I made the OH bond. Great, great, great. I still have on my list, make the carbon-carbon bond, break the CO pi bond. Okay, good. How would I do that? Well, the cyanide is electron rich. And surely, once this O is positively charged, that carbon is now increasingly positive. Now remember, it was delta positive to begin with. Why? It's attached to the O so that by induction, there's a delta plus charge here. But also by resonance, there's a plus charge here. So the combination of those makes this carbon quite attractive. Now that I put an O plus here, its ability to suck electrons by induction is now magnified, amplified. So that carbon is now very attractive. So I can see that the cyanide, can now target the carbonyl carbon and break the CO pi bond all at once. Because as I attack, the electron pressure from the negative charge in the cyanide pushes the electrons onto the O. Push, pull. When I do that, I end up with the cyanide, the CN group attached to what was once carbonyl, and I have O with a single bond H. Well, C single bond O single bond H, because I'm breaking the CO pi bond. So I can get both steps simultaneously, right? I can have, well, I shouldn't say both steps, both processes simultaneously. Make the carbon-carbon bond, break the CO pi bond. Now, I can draw it like this, which doesn't show stereochemistry, or I can draw it like this. Because this carbon is sp3 hybridized, so it's tetrahedral, so, which is the same as that. But I could have said, you know what? Maybe the way this happens is that I have the O, that species, and maybe what I want to do is to break the pi bond first. So I'm going to say, right, because what I did here is I made the carbon-carbon bond, which meant simultaneously breaking the carbon-oxygen pi bond. I did them synchronously. And maybe I said to myself, no. I kind of prefer that I break the pi bond first and make this species, which would put the positive charge on the carbon, and then have the cyanide attack, and the cyanide attacks, then I'm going to get my product. And that will be perfectly correct, except for one thing. This and that are resonance forms of each other. Right? Because this species, how did I go from here to here? All I did is I moved electrons. I did not move any atoms. So these two things are resonance forms of each other. So it means the only correction I would make is that I should draw a resonance atom. Which means neither this nor that is real. So for that matter, neither is this structure. I mean, that is just one resonance form. My point being, whether I do this or that, it's the same thing. Whether I say cyanide attacks the carbonyl-looking form or the carbocation-looking form, it is semantics, because neither form is real. They're resonance forms of each other. So this process is the same as that process. Okay? Let's do another one. Let's look at the reaction between this species and HCl, which gives as the products, let's say I get ethanol among my products and chloromethane. Well, I'm going to make it slightly more interesting. Okay. All right. Let's do that. Okay. So, what's happening? Let's get my laundry list of things. I have an ether, 1, 2, 3 carbons. It's reacting with HCl, and that's giving chloroethane and chloromethane, 1, 2, 3 carbons. So I accounted for my carbons. Where do I start? Make my laundry list. I've got to break the carbon O bond and make a carbon chlorine bond. One thing. I'm also breaking the carbon oxygen bond between the methyl and the O and make a carbon chlorine bond. So I'm doing the same thing twice. Okay. But I'm struck by a couple of things. One is that while there are 2 chlorines in the product, I only have 1 chlorine above the arrow. What does that mean? Well, what it's telling us this reaction is that the equation is in balance. It's not an equation. I am adding HCl, and I'm going to presume there are billions of HCl molecules. Right? So there are enough HCl's in the system to give rise to those products. Okay. But the other thing that I'm struck by is that my reagent, because I need to know where to start, so I know what I've got to do, right? Cleave here, make a carbon-chlorine bond and a carbon-chlorine bond. But what I'm also struck by is the fact that HCl is an acid. There is a mantra, there are 2 mantras that we want to burn into our consciousness. One of them, and we mentioned it already, so I'm going to add a part to it. So I guess it's one big mantra, is that acids do one thing, and one thing only. They protonate. Right? Acids are proton donors. The only thing that acids do is protonate. Okay. Who do they protonate? They protonate bases. Good. What makes me a base? And the answer is having either a lone pair of electrons or a pi pair of electrons. That's why we studied acid-base chemistry earlier. So acids do one thing and one thing only. They protonate. Who do they protonate? They protonate bases. What makes me a base? Having either a lone pair or a pi pair. So when I see HCl, HBr, sulfuric acid, or whatever above an arrow, I'm going to rejoice because I know step one. And you know why I know step one? Because we just said proton transfer between heteroatoms is the fastest and therefore the first reaction in organic chemistry. So if I do the whole thing from start to end, what do acids do? They protonate. Right? So acids do one thing and one thing only. They protonate. Who do they protonate? Bases. What makes me a base? Having a lone pair or pi pair. Proton transfers are the fastest and therefore the first reaction in organic chemistry. So I'm good to go. I look at this and I know that's an acid. Its fate is sealed. It's going to protonate somebody. Who? Somebody who's a base. Somebody with a lone pair of electrons. And the hardest thing with mechanisms often is, what's my first step? Well, it's telling you the first step, just because of who this is. So, the lone pair of electrons in the O acts as a base, attacks the acid. I'm going to break my HCl bond, we've done that a couple times. All acid-base reactions are equilibrium. So what do I get next? Well, I'm going to lose chloride. I always want to show atom balance. There's a chlorine here, I'm going to put the chloride here. And that's going to give me this species. That's going to give me this species, which is going to have a positive charge. And again, that is my oxonium ion. That's good. What happens next? Well, I've got to make some carbon-chlorine bonds. The chloride expelled in step one now recognizes these carbons as being exceedingly positive. Why? Well, they were originally attached to O, which made them delta plus, but now the O is positive, so you've enhanced the electrophilicity of you've enhanced the electronegativity of the O, so its ability to suck electrons from the carbons is magnified. The dipoles on those carbons are huge. So this O is going to pull electrons as a delta plus and a delta plus. O plus is going to pull electrons more. So I'm going to really have a significant pull, so the charges on these are going to be much, much greater. And if I had a choice of who to attack first, who would I attack first? Well, I'd attack that one. Why? Well, if the reason I'm attacking these carbons is because they're electron poor, they've got a delta plus charge, surely I'm going to attack the one that has a higher delta plus charge, all things being equal. That will have a higher delta plus charge. Why is that? Because it doesn't have an alkyl group. There is a delta plus charge. So remember we talked about carbocations, right? And why is it that a primary carbocation is unstable? Well, all carbocations are unstable. But why is a methyl carbocation not possible? Because there are no R groups to feed electron density onto this and stabilize it. Why is a primary carbocation not accessible unless it's resonance stabilized? Well, one R group doesn't dump electron density enough to stabilize that. Carbocations become possible only when they're secondary, so there are at least two R groups, better yet when they're tertiary. So the more R groups I have, the more they dump electrons onto the carbon, and that means the carbon gets less and less positive. So in fact, if I were to do this another way, I would draw it like this. So if this is methyl, the plus charge, I'll write it as the plus charge resides on the carbon. Right? The plus and the H is, but resides in the carbon. If I have primary, because the alkyl group pushes electrons onto the carbon, what this really means is if I'm pushing electrons, I'm losing electrons. So this R is the delta plus charge, which means the carbon doesn't have all the charge anymore. Maybe it's delta plus 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 plus. If I am secondary, and both R groups are dumping electron density in, well then both R groups develop a dipole. Which means the dipole on the carbon is only delta plus plus plus. And if I have a tertiary carbocation, where all of these are dumping electron density into the carbon, well then the dipole here is delta plus, delta plus, delta plus, so there's only a delta plus plus on that carbon. Right? So the dipole on the carbon drops as the number of alkyl groups increases. That's what stability means. What am I doing? I am diminishing the intensity of the charge on any one carbon. So nobody bears the full burden. And I am smearing the charge over larger and larger and larger surface areas. How do we stabilize a charged particle? We disperse the charge. We share the load. So what does that mean in this context? Both of these carbons are suffering from electron withdrawal. So if I say there's a delta plus 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 charge on this one, what's the charge on that? Well, it's got a methyl group. This carbon has a methyl group that feeds electron density onto it, which means this one is not as electron impoverished as that. That's only delta plus plus. So all things being equal, if chloride is looking for a soft place to land, a positive sign, I'm going to go here. The payoff is better. There's a larger positive charge. So what happens next is the chloride attacks the methyl group, push, pull. And I'm going to end up with methyl chloride, my first product, and I'm going to make the alcohol. So I've gotten one product. My laundry list now is getting good, right? I break the CO bond, I make the CCl bond. Good. But this is not my product. How do we get there? It's an alcohol. It's in a matrix that contains HCl. And it's not one HCl molecule. Right? I'm treating the ether with a sample of HCl. Look, there are billions of ether. If I give you a sample of liquid ether, there are billions of molecules of the ether. If I treat that with HCl, there are billions of HCl molecules in the mixture. In this particular case, I'll need to have two equivalents because I need to get two chlorides. So what will happen next is if I've got excess HCl, and maybe I should have said that it's excess HCl.